All right, good day. Hope that you're doing well. So in this video, we're going to be looking into question 9, right? We're moving on to question 9, and question 9 relates to Euclidean geometry. So now we're given a diagram whereby we're given a circle, right? BE with diameter, we're given a diameter BE, and we are also told that, okay, so basically we're given the points that are on the circle. And now I'm just interested in the questions. Now 9.1 says prove with the reasons that ABCD is a cyclic quad, right? So it means that, okay, let me just highlight ABCD so that you could see it, right? So we need to prove that this is a cyclic quad. Remember, there are three ways in which you can go about proving that something is a cyclic quad, right? So let us go through each of those three steps, right? Now, the first step is that if you could prove that an exterior angle, so if you could prove that an exterior angle is equal to the opposite interior angle, therefore this, let's name this ABCD. ABCD would be a cyclic quad. Second step, it's whereby if you could prove that opposite angles are supplementary, meaning that when you add them, you're going to get 180. Therefore, ABCD would be a cyclic quad. And the other one relates to when you're given a shape which is something like this, right? So if you could prove that this angle here, it is equals to that angle, you are proving that these two angles are equal, right? Therefore, this ABCD would be a cyclic quad, right? Your reason would be angles in the same segment, A and B. Now, here, let us see which way is more applicable with regards to this. Now, taking into consideration what we given here. So here, I can see that, all right, so let me just see. Now, firstly, I'm going to look at my given. I can see that here I am given this angle here as 90 degrees, all right? So I am given this angle as 90 degrees, meaning that, right? So if you could look at the shape that I have here, right? Look at this, and you could try and give it a guess with regards to which of the following scenarios, let me name this scenario A, B, and C would be applicable here, right? But then just to highlight this, if you could look at this shape, can you see that this would relate to this scenario C? So basically, what do I mean by that? So this here, we have a base, right, which is represented by this here. I'm going to erase afterwards, right? And we have these lines. These are the two lines, right? As well as these lines on the side, right? And already I was given that this is 90, right? It was given that this is 90 rather, meaning that if I could prove that this here, it's also equals to 90, therefore this whole thing would be a cyclic quad, right? So let me go about removing everything. Now, how would I prove that the other part is 90? Now, I was told that this line BE, it's a tangent, rather it's a diameter, not a tangent, right? And I know that angles that are created by a diameter, they are equals to 90 degrees. Now, as you can see, this diameter would create this angle here, A2. So A2, so I'm going to start by saying D2 is equals to 90 degrees. This was given. A2, A2 is also equals to 90 degrees. And why is that? This is an angle in a semicircle, right? So let me just go and do that. This is the angle in a semicircle. Now, with that being said, therefore, I can say, okay, D2 is going to be equal to A2, right? And as mentioned, because these two angles are equal to one another, therefore, ABCD would be a cyclic quad. ABCD is a cyclic quad, right? And my reason is that angle A2 and D2 are in the same segment, are in the same segment. So now the other questions, basically 9.2, it says prove with reasons that BD bisects uh, angle ABC. Now, this is my line from B to D. I need to prove given reason that it cuts this angle B into two equal angles. To be precise, I need to prove that B1 is equals to B2, right? Now, how am I? I am given this line as a tangent, right, to the small triangle, right? This is the tangent rather to the small circle, right? And what is my angle between it? This is my tangent and this is my chord, AE, right? The angle between my tangent and a chord is A3, right? If I were to draw AE, right? This is the angle between my tangent and a chord. And remember how I go about identifying tan chord? I use this as a shape whereby I'm just trying to make it relate to this shape that I have. This angle here, if this is the angle between my tangent and my chord, this would be equals to that angle here, right? And let me try and identify that here. This is my tangent, as mentioned. This is my chord, and this is going to be equals to this angle here, which is B1, right? So I'm going to start by mentioning that A3 is equals to B1 tan chord theorem. That will be my reason, right? Now let me just erase here. So I said A3, it is equals to B1. My reason is tan chord. But remember, we have just proved that ABCD is a cyclic chord, right? Meaning that we can assume that we have a circle around this. So let me just try and draw a circle. We can assume that we have a circle here. All circle theorems would be applicable. All right, so we can assume that there is a circle. Now, if that's the case, I want you to note something. So I have proved that A3 it is equals to B1, and also if you could look here, I have a butterfly, right? So let me just do this. Right? Can you see that this angle here, it will be in the same segment as that angle there, right? So basically A3 it's gonna be equals to B2, and my reason is because these are angles in the same segment, in the same segment. Right? So I've proved that A3 is equals to B1. I've also proved that A3 is equals to B2. Therefore, we can see that these two angles are equal to one another, right? B1 is equals to B2. Why am I saying that these angles are equal to one another? Because both of them are equals to A3, right? Therefore, we have proved that this line BD, it bisects those two angles. Basically, it cuts your angle B rather into two equal angles, right? So now let us look into the other questions that we're given. Now, proving that a line is a tangent to a circle. Now, there are also three ways in which you can go about proving that a line is a tangent to a circle, and I also want to write them here. Now, the first way is if you could prove that, so let me just do this. If you could prove that line from center is gonna meet, so let's say this is AB. If you could prove that my line from center, right, to circumference would meet with this line at 90 degrees. Therefore, AB would be a tangent, basically proving that this angle or that angle is equals to 90. This would make AB to be a tangent. This would be the first way. Now, the second way is your tan chord, right? Right. So here, remember my tan chord, how I identified is that this angle needs to be equals to that angle, right? So here, if you could prove that this angle between a chord, right? Remember, this is your chord, this is your tangent, it is equals to that angle there at the top. If you could prove that these two angles are equal, right? Therefore, this would make this line AB to be a tangent. So basically, here's your tan chord, right? And the other one, which you are most unlikely to use it, is if, remember, tangent from the same point are going to be equal to one another, right? Basically, if you could prove that this line is equals to that line, therefore, these two lines would be tangents, right? Because remember, tangents from the same points that are equal to one another. Now, let's look at the information that we're given. We need to prove that EC is a tangent. So firstly, I'm going to start by highlighting my line from E to C. So let me just erase here. Here's EC. So EC, we need to prove that EC is a tangent to circle OEF. Yes. So to circle OEF, right? That's the circle right over here, right? So let me also highlight this EC. Right. And if you could look into that circle that we have given, right, circle OEF that we are trying to make use of, can you see that we have a small triangle inside there, right? So we have this small triangle, and already this would give me a clue with regards to which of the three approaches I need to go about using with regards to proving that EC is a tangent, right? So already gives me a clue that I need to prove tan-cot theorem, right? So basically here, if I could prove that this angle here, so let me just erase this line here. If I could prove that this angle here, it is equals to O1, therefore EC would be a tangent, right? Remember, this is the angle between your chord, right? My chord, here's my chord, as well as my tangent EC. Now, how can I go about proving that? So let me look at what I'm given here. Now, I want you to see something. Look at BA. This is a four-sided shape in which its circumference are on the circle, the small circle, right? Four-sided shape in which its pointer on the circumference rather of a circle. Now, if you could look at this, this is a cyclic quad. BAEF, it's a cyclic quad. And if you could look at E3, this is an exterior angle of a cyclic quad. And what do we know about an exterior angle of your cyclic quad? An exterior angle of a cyclic quad, this would be equal to the opposite interior angle, right? So I could clearly see that these two are going to be equal to one another. So I'm going to say, okay, E3 is going to be equals to B1 plus B2. Why am I saying that? It's an exterior angle of a cyclic quad. It's going to be equals to the opposite interior angle, right? So meaning that if I could also prove that this angle here, so right, which is this angle here, if I could also prove that this angle is also equals to B1 as well as B2, therefore EC would be a tangent, right? Why? Because these two angles are going to be equals to one another. We are proving a tan-cot, right? Now let me see how I can make my O1 to be related to both those angles there at the top. Now I want you to look at something. Let's have a look at this here, this triangle here. Can we agree that OB is going to be equals to OF, right? So, okay, let me first write down what I wrote. So I wrote A3 is equals to B1 plus B2 because this is an exterior angle of a cyclic quad, right? So now, in triangle, OBF, which I've just highlighted in purple now, I know that OB is going to be equals to OF, radii. These lines are both radii, right? Meaning that I know that these two angles are going to be equals to one another, right? I know that angle B2 is going to be equals to F1, right? Opposite equal side based angles, right? So opposite equal sides based angles. Now, let's look at O1. O1 is an exterior angle of a triangle, right? So O1 is going to be equals to B2 plus F1, right? These two angles. Why? Because O1 is an exterior angle of a triangle. Exterior angle of a triangle, right? Now, remember, B2, it is equals to this angle, right? So B2 is equals to F1. But remember, we have proved that also in the previous question that B2 is equals to B1, right? So as a result, can you see that basically, technically, like O1, it will be equals to B2 plus B1, right? Because F1 would also be equals to B1. All these angles are equal to one another. So now we have proved that this angle here in the middle, it is equals to B1 plus B2. We have also proved that this angle between a chord, right, as well as this line we're trying to prove that is a tangent, it is equals to B1 and B2. Therefore, right, so we have proved that A3, this angle right over here, it is equals to B1 plus B2. And we have also proved that this angle here, O1, it is equals to B1 plus B2, meaning that these two angles are equal to one another. Therefore, line EC is going to be a tangent. And my reason would be tan-cot theorem. All right. And that'll be all for this video. Remember, if ever you have any questions, always feel free to reach out. Thanks.